Hi, I'm just going to work a problem out with you. This is in our slide deck, and it's in the section of 4.7, stoichiometry of precipitation reactions. So in the question, they're saying that we have 100 mils of potassium hydroxide, and it's 0.200 molar, and it's mixed with 100 mils of 0.2 molar magnesium nitrate. And ultimately, we're trying to get to the concentration of the ions that are going to be in the solution after the reaction. So the first thing you're going to want to do is write a balanced chemical equation. So you know that the potassium hydroxide and the magnesium nitrate are both soluble in water. And then it's a double replacement. We're going to get magnesium hydroxide and potassium nitrate. This is going to be my precip, the magnesium hydroxide. And then I would want to balance this too. So I would put a 2 and a 2. So my precip, I know if I use my SNAP method of remembering solubility, this doesn't have nitrate, potassium, sodium, or ammonium. So we can kind of infer that it is not soluble. The next question, the next step that I would do is I'm going to calculate the molarity of the compound. So I'm going to calculate the number of actually moles, let's do moles first, of potassium hydroxide, and I'm also going to be able to calculate the moles of the magnesium nitrate. So I can use the molarity equation and just solve for mole. I'm going to do it a little bit differently. I'm going to do it with dimensional analysis. Same thing though. So 0.000 of a liter times 0.200 molarity, which would then mean there's that many moles per 1 liter. So that gives me 0.0200 moles of potassium hydroxide. So you can do dimensional or you could plug into the equation, but either way, you're going to take the volume that's been given. So similarly with this one, and we're going to use that molarity to get the moles of each reactant. Then I want to figure out who the LR is and the ER, because the LR is going to get used up, and the ER, there's going to be leftovers, and we're going to have to figure that out when we're doing the concentration of all the ions. So you can get to the point now where you can reason through. You'd still need to write something. You can see that we need 2 times the moles of KOH for every 1 mole of magnesium nitrate. So you can see then that way that, oops, I lied. Why am I over there? Sorry. Oh, that was my precept. Sorry, I did say it right. So I can tell that I don't have twice as much of this potassium hydroxide. So my limiting reactant is the potassium hydroxide. My excess reactant is the magnesium nitrate. Next thing, I'm going to write a net ionic equation for the formation of the precipitate. So I'm going to take the magnesium that was aqueous plus the hydroxide ions, and then that would give me magnesium hydroxide. And that is my precipitate. So I can kind of start thinking about like what's in this solution mixture after the reaction. So I know that I have my magnesium hydroxide precipitate sitting on the bottom. And then I also know that, and you could write out the complete ionic if you can't see this, but I know the potassium and the nitrates are spectators. So my question is, how many leftovers magnesiums are there going to be? Because this is part of the excess reactant. So some of it's going to react and form magnesium hydroxide, but not all of it. So we can assume, because it was the limiting reactant, we can assume that all of the hydroxide ions have been used up. So the molarity of the hydroxide ions is 0 molar. But now we want to know the molarity of all the other ions. So the next thing that I would recommend doing is just like a normal excess reactant problem. I want to calculate how much of the magnesium ions are really going to get used up. And then I can subtract that from how much I'm starting with. So I'm going to, and so let's kind of talk about what we've done so far. So first, you always have to write a reaction. And then our second step was calculating the moles. So this would have been, step 1. Step 2 was figuring out the moles from the volume and the molarity of the two solutions. And then step 3 was writing out the net ionic. And I think, doing a nice drawing there. And now step 4, we're going to calculate the amount of magnesium ions we have at the beginning. So I'm going to start with my volume of my magnesium nitrate. You could start with your moles if you wanted, because that's really what I'm doing again. I'm using that molarity that was given. And then I'm also one more step though, my mole ratio, I have 1 mole of magnesium ions for every 1 mole of magnesium nitrate. So when I do this, I end up with 0.200 moles of magnesium ions to start with. So, as we always do with an excess reactant problem, when we want to know the amount that we really have left over, is we then need to calculate how much of the magnesium is going to react. So I'm going to start with my LR. So I'm going to start, and I could do the volume and the molarity, but this time I'm going to go just right with the moles from before. So I know that, and you could have done that up here too. Just started with moles of magnesium nitrate and went straight to moles of the ion. But this is my LR, so I'm going to need to switch over. So I know that in the balanced equation, I have 1 mole of magnesium nitrate for every 2 moles of potassium hydroxide. So just a normal converting to my excess reactant. The only difference is now I'm going to write that ratio, that I have 1 mole of magnesium for every 1 mole of magnesium oxide, nitrate, sorry. Hopefully I'm not saying that wrong throughout. So then that gives me 0.0100 moles of magnesium that are actually going to react. So step 6 is then let's figure out how much left over. So we're going to take our amount that we're starting with or given, and we're going to subtract how much of the moles of magnesium ions are going to react. And then that gives us an extra 0.01 mole of magnesium that didn't form a precipitate. And in the question, I'm asking you for the molarity of the ions. So the molarity of the magnesium ions would equal the moles of magnesium ion that are left over the total volume of the solution. So if you remember, each solution was 100 mils. So we had 200 mils, which is really 0.2 liter. So my molarity of the magnesium ion is 0.0500. That's the molarity of the ions that are left in the solution. So I just figured that one out. So my magnesium molarity is 0.0500 molar. So now let's figure out the molarity of the potassium, the spectators, and the nitrate. So we can do that by starting with our LR. So I'm going to start to figure out like my moles of potassium. I'm going to start with my, I'm going to start with my volume again of my potassium hydroxide. I could start from mole again, but I'm having fun doing these conversions. So I'm using my molarity again. And then I'm going to change it over. There's 1 mole of potassium for every 1 mole of potassium hydroxide. So that gives me 0.200 moles of potassium ions. So then the molarity of the potassium is going to equal those moles over that total volume again. And then that gives me 0.100 molarity. So I'm going back up. So I know the molarity I know the hydroxide is 0. There's none left over because all of the hydroxide went into the precipitate because the potassium hydroxide was the limiting reactant. Then I have the solution part. I know I've got my spectators in there. And then I also have my excess magnesium ions in there. That's why we had to calculate the amount of magnesium that was used versus what we started with and subtracted. So let's do our last spectator. We're going to do nitrate. And I'm going to give myself more room. So really similar. We're going to start with, and again, you could start with mole of, I'm trying to figure out how many moles of nitrate I have. So I'm going to start with the volume that was given in the beginning. And then I'm going to use that molarity. So like I said, this is equal to moles. So you could just go right to mole that you have from previous question. And then we do need to realize that there's 2 moles of nitrate for every 1 mole of magnesium nitrate. So then when I calculate this, I'm going to get 0.400 moles of nitrate ions. So the molarity of the nitrate is going to equal the moles of the nitrate ions in the solution, which remember it was the 100 mils of each reactant. So that's why, and then I'm converting to liters. So it's really dividing by 0.200 liter. And so when I do that, I will get 0.200 molarity. So there's 0.2 moles of nitrate per liter of the solution. So back up here, 0.2. So I hope that helped you understand, what's left over in the solution, and we can figure out the concentration of that. And I'll review it one more time. If you're done and you understand, then you can just quit the video. But so basically, you're mixing 2 things together that are aqueous. You're forming a precipitate. Otherwise, the reaction wouldn't happen. Then you can reason your way through who the LR is by looking at the mole ratio after you've calculated the moles of each reactant using their molarity. So I have 0.0200 moles of potassium hydroxide and the same number of moles of magnesium nitrate. They are going to react in a 2-to-1 ratio, so you can see that you don't have enough potassium hydroxide. You would have to have 0.04. So that means the potassium hydroxide is the limiting reactant and the magnesium nitrate is the excess reactant. Then you want to write the net ionic equation, because that is the real overall reaction that's happening. The rest of everything is just spectating. And so we know that the hydroxide ions are going to be completely used up because that is part of the limiting reactant. And we know we're going to have some excess magnesium ions because that is the excess reactant. We could also calculate the grams of precipitate. We do that in another problem. It's not that hard, but for this problem, we really want to know then what is the molarity of the spectators and that leftover magnesium. So what I did is I calculated my moles of magnesium, which I had done previously, so you could just start with that number here. And then I calculated the moles of magnesium ions. And this is how much I had to start. So I'm calculating how much of the magnesium I had in the beginning. Then I want to calculate how much reacts. So this one, I do want to start with that LR. And again, and then I would convert over to the magnesium nitrate, but then I would want to know that there's 1 magnesium for every 1 magnesium nitrate. So that gives me 0.0100 moles of magnesium are actually going to react. So I'm going to subtract that from the beginning amount. So I'm really taking these and subtracting to figure out how much excess reactant, how much excess moles of magnesium ions. And then lastly, I'm going to calculate the molarity by taking those moles and dividing by the total volume of the solution. So where did I get this? I got this from the beginning question. They tell me I have 100 mils and 100 mils. So I really have 200 mils, which is the same as 0.2 liters. And then to figure out my spectator, I'm going to, again, I could go right to moles that I had previously calculated. And then I would do a ratio of the potassium ions to the compound. Again, this is moles. I want molarity. So I have to divide by that total volume. And then I would get 0.1 molar. For the potassium spectator, none of that got reacted, so we don't have to subtract or anything. And then the same thing similarly for the nitrate. Start out with your moles of magnesium nitrate, and then you have 2 nitrates for every 1 magnesium nitrate. Then you would take your moles again and divide by molarity.